So I would like to talk about life cycle assessment or carbon footprinting, a subset of LCA, and the uncertainty that is incurred by certain methodological choices that the practitioner does. So I have here an overview of why we are interested in biofuels in the first place. So they came as a strategy. It was deemed that the use of biofuels as a replacement for fossil fuels were deemed as a proper strategy for climate change mitigation. So that was the starting point for all the attention that biofuels have received over the last 20 years or so in Europe and also in the US and in other parts of the world. At the same time, the need for assessing the climate impacts of bioenergy systems became obvious. It was not just about the carbon or the CO2 that was emitted at tailpipe, but also all the emissions that took place in order to have that biofuel produced. So life cycle assessment was elected as the appropriate tool with which we could measure these life cycle greenhouse gas emissions. But the application of this tool incurs in a big level of uncertainty, which means that individual estimates tend to be very variable depending on who conducts the study or who does the methodological choices that you need to do whenever you do an LCA. So I want to talk about these issues that are still unresolved in the carbon footprinting of biofuel systems, but in LCA in general, because they really are the reasons why results vary this much. So let's dig into that. And then finally, I will conclude with some insights and prospects in terms of the uncertainty and relevance of LCA for decision support for biofuels or renewable energy in general, or just the transition towards more sustainable production and consumption systems. One might be led to believe, especially 20 years ago when this whole debate initiated, that bioenergy is carbon neutral. This is because the carbon emitted or the CO2 emitted upon combustion is the same as the carbon that was sequestered via photosynthesis as the biofuel feedstock grew. So far, so good. However, this simplistic notion of the system excludes a bunch of things that we now know that we have to take into account in order to make an appropriate assessment of bioenergy and really decide, have a scientific basis to decide whether we should be promoting biofuels or not. So if biofuels do incur in fewer greenhouse gas emissions than their fossil fuel counterparts, then sure, let's promote them. But do they really? So the question is how we actually know whether biofuels ought to be promoted or not. But we at least do know that bioenergy is not carbon neutral, even though the biogenic parts of the bioenergy may balance out if it's at least not released as methane and as CO2. But then in order to get the biofuel in the market, you need to grow it, you need to cultivate land, you need to apply agrochemicals, you have land use change that needs to take place in order to make way for the energy crop. You have albedo effects, you have non-CO2 greenhouse gases. So no, bioenergy really is not carbon neutral. It may be carbon positive, it may be carbon negative, but it's certainly not neutral. This is already known for many years. There's nothing new here. What was interesting to see almost 15 years ago, I think, was that LCA as a tool with which you can add the emissions that occur at the different life cycle stages of any product, of a biofuel product, is really what you need to estimate in order to say something useful about the biofuel's ability to mitigate climate change. And this was already known in 1997. This was a long time ago. It wasn't actually called life cycle assessment. This was work produced by Bernard Schlamadinger at IEA Bioenergy, where the emissions of the bioenergy systems were the emissions that accumulated over the course of its life cycle. And if you wanted to have a useful comparison, you would have to do the same on a fossil fuel comparator across the same functionality. And then, yes, then you could say something useful about whether biofuels saved on greenhouse gas emissions or not. And here on the right-hand side, you can see what Horst has already shown in his presentation, which is that the total emissions of a biofuel should be estimated as the addition of the emissions occurring at the different life cycle stages. This is in Annex 5 of the Renewable Energy Directive, which was indeed a very big encouragement to the LCA community that what we were doing was relevant also for policymaking. So with this application, the application of this approach allowed the European Commission to know and distinguish the feedstocks that met certain criteria from the feedstocks that did not. And in the original Renewable Energy Directive of 2009, the aim was to save 35% greenhouse gas emissions relative to fossil fuels. And with the application of LCA, we were able to determine the amount of emissions saved and whether they abided by the targets or whether they were under the threshold of GHG savings. And you could see here that for three very popular biofuel feedstocks, so wheat, soybean, and palm oil, the first for ethanol and the second two for biodiesel, the emission savings did exist, but it was not enough to meet the 35% threshold. So then the European Commission knew that these three feedstocks should not be supported because they didn't meet their preconceived targets, while others did in this case. This is data from the JRC just to show you the life cycle greenhouse gas emissions of different biodiesel feedstocks for HVO and FAME. And you can see how this compares with the fossil fuel comparator, which has ranged between 85 and 95 grams of CO2 equivalent per megajoule. So that line you see there represents the emissions from whatever the biofuel is displacing. So 1 megajoule of, oh, something is happening in my slides. Anyway, that's the level of fossil fuel emissions. This is the original level in the directive, so 35% savings. And you can already see that some biofuel feedstocks do not meet this criterion. But with time, with RED 2 and 3, this target became increasingly ambitious. So if in 2010 we had 35% savings as a minimum requirement, in 2017 you had 50, and then 60, and then 65% savings in 2021, like Horst mentioned. But then from 2023 onwards, the minimum level of greenhouse gas savings is actually 70%. So it's extremely ambitious, meaning that fewer and fewer feedstocks will be eligible for European Commission support. And the same for bioethanol. In fact, from 2023 with a 70% savings requirement, there's only 1 or 2 that actually meet this criterion. So with this, I point out that life cycle assessment and the life cycle assessment approach, which is what you adopt when you do a carbon footprint, is needed in order to tell us where to go, which bioenergy feedstocks we should be promoting and which ones we should not, because they don't meet what we want them to meet. And this is a piece of work I've published last year, where I also try to estimate the carbon footprint of different biofuels with European Commission's data, with the same data as in the Renewable Energy Directive, but doing it in slightly different ways. So you have the default values where I added direct land use change, but also indirect land use change, which in some versions is mutually exclusive, and according to some interpretations, it is not. And also with an attributional and a consequential approach. And you can see here that the range of estimates is actually quite large, at least for some of the feedstocks. So the question really is, why do values vary all that much? And here you can see a chart published by the IPCC, the Renewable Energy and Climate Change Mitigation Special Report. And you can see that results are very variable for fossil fuel feedstocks, not so much for nuclear energy, even less for renewable energy. But then for biopower, or what they call biopower, which is liquid biofuels and bioenergy, the results are not only extremely variable, but they vary from positive values to negative values. So clearly something needs to be addressed in the way in which we calculate these carbon footprints. So I've done some work on this, and what I think what it boils down to is that people who conduct these carbon footprints have different goals and scopes. They do things different. So there's two issues within the goal and scope definition from which results may vary. And then there's one related to life cycle impact assessment. So these are the characterization models that are used to characterize and find a common denominator between different greenhouse gas emissions, and also the timing of the different fluxes. Within the first set of issues, I think the use of attributional modeling or consequential modeling, which in turn determines how the system boundary is delimited, very much affects the results generated, particularly because it determines how you deal with co-production. So in attributional LCA, you usually refer to allocation. You create somewhat arbitrarily an allocation key for dividing or partitioning the burdens between two product systems. And in consequential LCA, you use substitution, which in my view is far more relevant for supporting decision-making, particularly at the policy level. And then the second issue within the goal and scope definition is what you decide to adopt as a reference system for land use. Most LCA studies don't adopt any reference, but if you don't use land for something, you might use land for something else, or it might be allowed to regenerate or relax, as we call it in life cycle assessment, and therefore that is the appropriate measure against which you should assess your biofuel production system. And on the second level of concerns or uncertainty, you have different characterization models like global warming potentials that give you different answers. And this is indeed another source of uncertainty that I will also talk about. On the modeling side of the equation, you have two large approaches which are competing. Just as a warning, I belong to the consequential approach, but there are several definitions for each of these competing modeling approaches. I chose this definition because I find them more complete and more mutually exclusive. So an attributional approach is a system modeling approach in which inputs and outputs are attributed to the functional unit of a product system by linking and or partitioning the unit processes of the system according to a normative rule. I've highlighted the bits I find relevant here. And this normative rule would be, for example, to base your allocation key on the relative attributes of the co-products. For example, the energy content or the mass content or the economic value. Alternatively, you have the consequential approach, which is a system modeling approach in which activities in a product system are linked so that activities are included in the product system to the extent that they are expected to change as a consequence of a change in the demand for the functional unit. I've got to apologize. I know this is a mouthful, but these really are the most elegant definitions I've come across. And if you want to see this in an illustrative manner, you can see that while consequential approaches, they model additionality. So whatever happens as a result of your decision at the margin, in addition, as well as whatever may be displaced as a consequence of your product system. And in attributional LCA, you partition emissions between different economic activities. And like our colleague Rich Plevin pointed out, using attributional LCA to estimate climate change mitigation misleads policymakers. And I wholeheartedly agree with the title of his paper. So if you apply approaches, so you have 4 approaches being applied to every stock. The first 2 are the ones renewable land active with direct land change and with indirect land change. And then you have the attribution approach, and finally the consequential approach. In this slide, you can really see how results vary depending on the modeling approach applied. And one of these issues is related to how you model indirect land use change, which many of our colleagues still think does not happen. It's not real. So I have here an example that shows you, for example, when you convert grasslands to annual cropland in order to, for example, grow feedstock for ethanol, you incur direct land use changes because grassland would have a higher carbon stock on land than wheat. So that's the direct land use change part. It's easy to measure, it's verifiable. And usually you divide the total emissions of the subsequent 20 years of cropping in order to attribute a particular value to 1 year's worth of cropping. But in addition to these impacts, you have indirect land use change impacts, which is where the grassland, which used to be fed to livestock and is no longer, does not mean that the livestock will no longer be fed. So that livestock will have to be fed in some other way. And the most likely way, the marginal way, is that soybean meal or soybeans would have to be produced, probably in South America, and likely at the expense of rainforest conversion with high carbon stocks associated to that. So these are the elements of the reference system that needs to be taken into account if you really want to do a complete life cycle assessment. And fortunately, the EU commissioner did understand this, and she actually said when the ILUC directive was published that some biofuels receiving EU subsidies are as bad as, or even worse, than the fossil fuels they replace. So how do we actually estimate indirect land use change emissions? It's notoriously difficult. This shows you just the range of values from -200 to +600 grams of CO2 equivalent per megajoule. So you can see that the range is extremely large. And it doesn't really help decision makers adopting a specific value that they feel confident with. So what the European Commission did was to go with the IFPRI model, and these are the factors they have adopted. Well, they didn't adopt in policy, but these were the ones that were more recommended above others, let's say it this way. Here I want to show you a study where I try to model the climate change impacts of producing ethanol from corn in the US. So the US government has this target of 15 billion gallons of ethanol every year, which translates into 45 million tons of bioethanol, which displaces gasoline. So far, so good. But then what does it take in order for these 45 million tons of bioethanol being produced? So I tried to estimate this consequentially, where this corn would come from. Some would come from existing land, some would come from expanded land, some would be diverted from other markets, for example, the animal feed market or the vegetable oil market, and others even from food. And also you have to include that when you produce bioethanol, you produce dry distiller grains with solubles, which is also used as an animal feed. So we had to balance different markets to make it right. And the results are here. So you can see that large emissions are avoided from the avoided use of gasoline and also from the avoided soybean cultivation, because when you grow when you shock the feed market with DDGS, you also avoid alternative feed production. So those are the benefits of the policy, which are not insignificant. But then if you take into account the additional emissions that take place, also because of the balancing of those markets, then you realize that for climate change mitigation, using bioenergy, using ethanol from corn in the US is actually not a very effective policy. And this is related to the third factor upon which uncertainty lies, which is the impact assessment models. And depending on which one you use, some of these I created myself, some of these models, bioenergy may either be better or worse than the fossil fuel it replaces, depending on how you assess the timing of emissions and the asymmetry with which carbon is either sequestered or released. And this basically summarizes the different sources of uncertainty. It was also published last year. So I know I'm running a bit over my time. I would just like to conclude with this slide and perhaps the next one, which is to say that uncertainty and precision are two different things. You have here a situation where the precision is very large, so the values are not variable, they're very close to one another, but very far from the bullseye. So the results here are biased, while here you have a high accuracy of estimates, but the precision is very low because all these estimates are very far apart from one another, but you could be said to be having representative results. And like I tell my students, it is much more important to be able to survey the set of possible systems approximately than to examine the wrong system exactly. It is better to be approximately right than precisely wrong. I really think we need to have this in mind whenever we do our models. So my final slide is this, the carbon footprinting of biofuel systems. Carbon footprinting is very relevant and its relevance is growing. There are ISO standards, there are several guidelines. Perhaps this proliferation of guidelines is actually not that useful, which represents a lack of consensus in the scientific community about how to actually carry out a carbon footprint. So in my mind, we need increasing harmonization in LCA practice. But we have derived some insights when applying the carbon footprint to biofuel systems. And the first one is that they are not necessarily better than the fossil fuels they replace, but doing a proper carbon footprint allows us to identify the worst from the best. And that's why biofuels may still play a role in climate change mitigation, and so does the tool itself, carbon footprinting. I would also like to say that methodological choices do determine the results, particularly because they define how the system boundary is set and whether indirect effects are included or excluded. And finally, I would just like to say that all models are wrong, but some are useful. So we need to do all these complex decisions, and LCA and carbon footprinting can help us making the right decision, but we need to do it in a way that we do not shift burdens where we cannot see them. So thank you very much for your attention and apologies for running over time. I think we have 1 minute left for questions. I'm going through the box. Okay, regarding the slide with the variations in carbon footprint, were these values for the same biofuel, raw material, process, and location? No, they were not. Location, yes, it refers to Europe, unless we're talking about palm oil, which refers to Southeast Asia, mainly Malaysia and Indonesia. Because if it wasn't, I'd really expect a big variation, since it depends on biomass and varies a lot depending on the parameters mentioned above. You are correct, but these variations that I've been showing relate to the choices that a practitioner of carbon footprinting makes. So how to deal with co-production, how to deal with land use change, how to deal with indirect land use change, and not necessarily within of agricultural systems.